for the patience. I'm Alberto Casagrande, I'm your teacher of computer programming. And to be honest, I'm quite excited because this is the very first time since the last year I'm giving a lesson in presence. So, as you may imagine, is a novelty also for me. And besides this, it's a weird class, this one, because it's the very first time we are going to have a mixed modality for the lesson. At the same time, we are going to have students in the class, and we are streaming online everything. Okay, so it would be tough for me. So I kindly ask you to be patient with myself, and we will try to tune everything during the lessons. Okay. So if from time to time I'm not focusing on you, please raise your hands and tell me, look, you are speaking to the YouTube guys and not with us, and hopefully the other way around will work in the very same way. So this is it. Do you have any question about this course? Not yet. Well, wonderful. So let me go to the slides then, and to my presentation, which is here. So, as I told you, my name is Alberto Casagrande, and this is the pre-course of computer programming. So here you can see my, whether I'm, yeah. Here you can see my email address, which is the main way by which you can contact me, and my office, which is at the moment totally useless, but eventually will become good information for you to come to have pieces of information about the course or advices or whatever you want. Okay, and what is about this course? Well, this course is about something that I like to call the art of computer programming. Computer programming is something I can teach you in some way, but not completely. Okay, it's more like just like painting. I can tell you how to paint by using I don't know, wonderful color. I can you how to paint like Picasso. I can tell you how to paint like Van Gogh. But unfortunately, I cannot teach you how to be a master of painting. Okay, and exactly in the same way, I can teach you how to write program from a syntactic point of view correctly, but I cannot teach you how to imagine a new program. Okay, and that's the tough part. And for being a master in computer programming, you need to exercise. And this is just in your hand, okay? It's not due to my teaching, it's not due to what I'm going to tell you, it's just exercise. And you have to exercise to reach a certain level of ability in computer programming. Besides the computer programming part, we will see also some useful notions and tools that you are going to use during the DSCC program. And for instance, I don't know. Well, let me go through all the point. First of all, we will see what is a programming language. So from the very scratch, we will introduce it, as you never saw it before. Okay, and we will see how what is called source code is related to the program you are using right now on your mobile or on your computer. And we will see some fundamental problem-solving strategies. So I show you some encoded, let's say, way to solve problem. Okay, so if you have a certain kind of problem, you can try to solve it by using that strategy. That's basically the idea. And we will see also few basic notions on operative systems. Unfortunately, you cannot see all the slides. I'm sorry for you. And what is called shell, which is basically a user interface based on text. So instead of using mouses and I don't know, Windows, let's say, you are going to write commands on a shell, which is a command line user interface, and you will get some kind of results by executing this command on the shell itself. Okay, so we'll see many things. The most important thing to know, to remember, is that at the beginning of this course, no prior knowledge is really needed. Besides, I don't know, what is a monitor, what is a keyboard or something similar, okay? Besides this, I'm not requiring any previous knowledge of the topic. And let me see. Oh, good morning. Okay. From time to time, I'm stopping my lesson just to see whether there are comments online. Okay, so please be patient. As I told you, this is my very first experience in the mixed mode teaching, so we will tune in during the course. So going back to my slides, as I said at the very beginning of the course, I'm not going to ask you any previous knowledge of the topic, and I'm going to tell really trivial things from a certain point of view. So don't be scared from the fact that I'm telling naive stuff to you. Okay, I'm teaching naive stuff. By the end of the course, probably you will see something you never seen before. At least I hope for you. Okay, and this is the suggested textbook concerning the C programming languages. It's a quite old book. This is probably the first, well, for certain, this is the first book in on the C programming language, and actually it was written by Ricci and Kernighan, which are basically the parents of C. Okay, and you don't need, technically you don't need it, okay, because I'm going to tell you everything you really need to know. But if you would like to buy a book, this is the book for the C programming language. Okay. So all the course material, including the slides and I don't know, some suggestion about online book exercises and so on, will be released on Moodle. Moodle is a, let's say, site, let me call it in this way, on which is used by this university to publish all the course material. Okay, and you can try to search on Google Moodle UniTS Casagrande, and you will land on some of my courses, or you can just remember this ID and by using it reach the material of this year. Okay, this is it. So how are we going to learn? Well, of course, we will have a front-end lesson as we are going, as we are having right now. We are having it right now, and so in-person lesson. We will have a streaming lesson, as your colleague at home are experiencing. But all the lesson will be recorded and released publicly on YouTube. Okay, so if for some reason you are not going to come to one lesson, don't worry, don't be scared, because you have another appointment, I don't know, a doctor, I don't know, please, but let's say you need to go to the doctor, then you can receive all that lesson online by your own. Okay, and this is it. We will see some example of code. So during the lesson, we are going to experience how to write code by looking at some examples. So I will say something like, how can we write a program to compute this stuff? And we will see part of it during the class. And there will be some exercises that you are required to solve by your own method. Okay, and okay, this is what I said before. As I said, I'm going to require the homework. So I'm going to require you to do all the homework, but I'm not going to evaluate that. This is just to let you taste really what's going on with programming, computer programming, and to understand your level by your own. Okay, so if at some point I will give you an exercise and you will try to solve, and you try to solve it and you end up in a failure, don't worry. It's somehow expected. Okay, this is just to be conscious of what you can do and what you cannot do at the moment. But eventually you will be able to solve any problem by your own, of course. Okay, so when are we going to have all lesson, all the courses, all the complete schedule of all the courses for the first semester for the DSSC program is available at that URL. Okay, so you can reach it by going to the DSSC site, student something, and then from that you get a lecture plan. So you may wonder, why are we going to learn computer programming? Why it's so necessary to learn computer programming? Especially you are here to handle data. You are not here to program. Okay, so why is so necessary to learn computer programming? Well, the point is that computer programming is a good exercise for you, and besides the exercise, it's a good exercise to practice in analyzing a problem and try to find a way to solve it. So in general, these two tasks can be applied to any domain of our knowledge. So if you are working in business, for instance, you need to understand what's going on and try to plan a solution for it. If you're a farmer, you need to understand why your culture had many problems last year, and you need to find a way to manage the problem, and so on. And these two tasks can be exercised by using computer programming, because computer programming is, from a certain point of view, really easy to handle. It's much tougher to understand what's going on with the future, rather than, by future I mean business future. Okay, so on Wall Street stuff and so on, rather than understanding why computer programming is not giving you the right answer. Okay, and but however, it's a good exercise. Moreover, computer programming is necessary to achieve boring stuff, which are harder for a human being. So if I ask you to sort, for instance, 1 billion number, of course this is a quite hard task to be achieved from a human being, but not that hard for a computer. So learning how to teach a computer how to solve a problem is a good idea, especially if you are going to handle a massive quantity of data. Okay? And learning computer programming is especially important to improve the efficiency of the activity which you are going to do, you are going to achieve during your presence on this program. Okay? And okay, this is probably not your case, but you may have fun in programming. Okay? And last but not least, survive the SSC program. Okay, if you know how to program a computer, probably you don't have many problems. You are not going to have many problems in the SSC program. The other way around is for sure false. Okay, so if you don't know how to program a computer, for sure you are going to have a problem in the SSP program. Okay, so now how much should I study to learn computer programming? This is a tough question to answer because it depends from person to person, of course. So from my point of view, it's much easier to, I don't know, learn a new programming language rather than, I don't know, play a basketball match. But it depends on you. Okay, it's a quite personal question. But let's try to give a general answer. So how many of you can speak Vietnamese, for instance? None. Okay? So none of you can speak Vietnamese. So, and how much time do you think it's needed to learn Vietnamese? So please give an estimation. I don't know, for you, for instance, how much time is required to learn Vietnamese?
Depends on the level, but a lot.
A lot. I mean, days?
Years.
Years, okay, years. Yes, it's a good estimation, especially because Vietnamese is for sure not a language, Latin-derived language, so it's far away from our language. Okay. Well, programming languages are for sure easier than Vietnamese, but they are languages. Okay. And so it may take time to completely be self-confident on programming a computer. Okay, as in natural language, there are families of computer programming language which are quite similar. So once you have learned one of them, learning the other ones, it's easy. Okay, but starting from the scratch, learning the very first programming language might be a little tough. And that's why I'm telling you that you need exercise, okay? And that's the tougher part of learning how to program a computer, because I cannot teach you how to have exercise, okay? I can only give you exercise and say, please do it, okay? That's it. So what about the exam? Well, as you probably may know, pre-courses do not have exams. Okay, so party, yes, but unfortunately, many will come. Okay, and many of these courses during the DSS-C programs, will assume that you already know how to program a computer. Okay. So no exam for this course, but this course may be quite useful, especially if you never experienced before computer programming. That's it. By the way, how many of you have already experienced computer programming? All of you. Nice. So how many of you have experienced the C programming language? Okay, Java. Okay, Python. Okay, Visual Basic. Okay, what about you? Fortran. Ah, okay, Fortran. Okay, great. So any question about what I said until now? Not really. It was so clear. Oh, strange. Okay. And what about you? Okay, good morning. I have another question. Why C and not other languages? A part of Python is very useful for data analysis, for example. Thanks. So some of your colleagues is asking why we are focusing on C, on the C programming language, and not on Python. Well, the point is that Python is a really high-level language which assumes many things about what comes under, so near the, let's say, hardware thing, okay? And this is nice, but from a certain point of view, if you learn directly Python, you are going to miss a lot of useful things which are useful to program in Python. Moreover, since you are going in this program to use clusters, okay, there are many kind of clusters, but some of them basically explicitly require you to program in C or C++. Okay, so very low level programming. Not very low level, but I mean not that high, such as the Python level. Okay, and so in order to exploit at best this cluster, knowing how to program in C and C++ is quite useful. This doesn't mean, for instance, this doesn't mean that you are going to always program in C or C++, which is a sibling, let's say, language of the C programming language. Just to let you know, probably my last project in C was, I don't know, I think 10 years ago, okay. And since then I was programming in, I don't know, Python probably is my most used programming language, and other stuff. But despite this, I really think that knowing how to program a computer in C is quite useful, okay? And can teach you a lot of things that you really need to be a master in computer programming. And this is it. I hope I answered to your question. So, okay, let's move on. So what are we going to see during the last, well, not the last, but the next part of this presentation? We are going to understand what is a computer, okay? We are going to understand what is a program, but probably you already know it, so there shouldn't be any problem. We are going to understand how computers do encode data and programs, so how they are really represented inside the computer, and what is a programming language. What are programming languages? Okay, this is it. So let me move to the next slide, or rather to the next slide batch. Here we are. So let's start with a very introductive set of slides about the concept. The very first thing to understand is What is that? Can you guess what it is? A microwave. Who does agree with your colleague? Is it a microwave?
Yes.
Okay, who doesn't agree? No. Okay, so this is a microwave, right? And what is this?
Desktop, a computer,
A computer. Okay. Yeah. Well, it's a computer with a keyboard, a mouse, and a monitor. Okay. So, do you know what's the main difference between these two electronic equipment?
The microwave is created for a specific purpose. They're both got some electronic components, but the computer can be used for a bigger, high amount of different things, while the microwave can only do one specific thing.
Well, I wouldn't say so, because I mean the microwave can be used to, I don't know, eat your meal, but also eat something. So you can throw the microwave to someone. Sorry. You can use it as a chair, for instance. So it's not really true what you are saying. So the microwave is built for just one task and the computer for many. It's not really, I mean, you're almost there, but this is not the true
computer
answer.
handles like user interface, so you can tell it what to do, but the microwave can't.
Well, what about a smart microwave? Or a smart, I don't know, a fridge, in which you have a monitor and you can tell him, look, I'm missing eggs, please order my eggs. I mean, don't be focused on the very specific kind of microwave, because of course, I mean, this is probably older than me. I think so, at least. I hope so, at least. But I mean, the point is not really on the how smart is the electronic equipment. Again, you are almost there, but that's not really the point. Any other idea?
Their function?
Pardon?
Their function?
Can you repeat it, please?
Function. What are they built for? Microwaves are built to eat things, which is the main task for the purpose for which it is built.
Mm-hmm.
And computers are built to evaluate things.
Okay, I guess you've never been in a server room, because it's really, really hot.
Yeah, but it's a side. It's a side.
A side effect. Okay, that's true. Okay, again, you are almost there. Well, the point is that computer program can achieve new tasks. So when you are building a computer, you don't know what task it's going to solve. And you can teach to solve new tasks by programming it. While the microwave cannot be programmed. Well, you can tell him it to heat your meal at 1 p.m. or 2 p.m., but that's all. Once the production ended, all the feature of the microwave is already present in the microwave itself. Okay, so the main difference is that you can teach new tasks. Let's say teach. It's not really teach. It's program new tasks to the computer. While the other electronic equipment cannot be taught to solve different tasks from the one they are built upon. Okay, so you were almost there, all of you. So if you want to solve a new task, you don't need to change a computer. You change it just because you want a brand new computer, okay? Or it's broken like mine. But the other way around is not true. Okay, so if you want to achieve a new task, to solve a new problem in your computer, just install a new program. We are always experiencing this kind of thing when we install new things on our smartphone. So if you install a new app on your smartphone, you end up to solve a new problem or to play a new game. More or less it's the same. While the opposite is not true, of course, for the microwave, so please don't try to dry the carton in the microwave, because it's dangerous, okay? Okay, so now we understood that a computer can be taught to solve a new problem, but how can we teach it? By using programs. But what are programs? So there are many definitions of programs because it really depends on the way you intend a program. But as far as we are concerned, it is a sequence of instructions that hopefully, eventually, lead the computer to perform a named task. So we want to solve a new problem. And to do it, we need to how can I say, list a set of instructions and let the computer understand that instruction to perform all the operation we need to perform to achieve that task. Okay? That's the idea. But you already know it because you're already familiar with the notion of program. Oh, by the way, you're already familiar with the notion of program of the imperative program. Okay, so the programming language you mentioned before are programming languages named imperative programming languages, which basically means that the program are intended as sequence of instruction, just like in our case. But there are different kind of programs which are not meant to be in this way. Okay? So they are more or less exactly the same. So the point right now is, what is an instruction for a computer? So we know we have to list a set of operations to be performed to achieve our task, but what kind of operation can we use? For instance, an operation, can the operation please go to the grocery and buy me a milk can be performed by a computer? Not really. Okay, this is a quite complex task which must be actually split in small, simpler subtasks to be achieved. Okay, so what we intend by using the word instruction. Well, to answer that question, I need to introduce what is called von Neumann architecture. So von Neumann was a scientist, actual mathematician. He was quite famous in many fields. For instance, probably, well, for sure, he also works to the Manhattan Project, which was the project of the very first atomic bomb, and it was involved in the development of the second electronic computer in US. And since he was working with many engineers, they were great in developing electronics, but there are a kind of mess in understanding what's going on from an high level. Okay, so he proposed what is now known as von Neumann architecture, which is a design, a kind of design, a schema for a computer machinery, which is also used nowadays, still used. The idea is to have more or less a central processing unit or a CPU, which is going to perform all the operation, a memory, which is meant to store both data and instruction, and some kind of input-output mechanism, just like monitor or keyboard or mouses or so on. Okay? And this is the von Neumann architecture. So the idea is that the instruction for building programs and at the same time the data upon which the programs should must operate, must be stored in the very same place. Okay, so internally our computer must represent them in the very same way. And by the way, as I said, this architecture is virtually implemented in any possible computer implementation. So for instance, in your smartphone, in your laptop, in your monitor, and I don't know, every single stuff is using a computer. Now, let's focus a little bit in memory. So what is a memory for computer? A computer memory, let's say, okay? So a computer memory is just like a space in which we can place both program and data. But of course, we need to retrieve all the programs and the data we are storing in memory. And so to do it, we need to indexize in some sense. So we need to label all the part of the memory in different way, so that once we need the number we stored before, we can find it. And to do it, we use addresses. So the memory is just like a parking stall. Okay, just imagine a parking stall in a mall. You know that when you arrive in the mall, you park your car in the stall number, I don't know, 13. And to find your car back, you simply have to reach the stall 13. Okay? And this is the idea. So we have a place, and this place is split in different stalls. And the number below the stalls is named address. Okay? And so if you have a red car, you can park your car in the stall number in the address number 1035, and that's okay. To find the car, you simply have to go to that address. But what if you don't have a car but you are driving a bus, for instance? Well, of course, the single stall is not enough to store the whole bus. So how can you do? Well, you can use many stalls. Okay, and now you know that your bus is in stalls number 1036, 37, 38, and 39. And in the very same way, if you have data which cannot be represented in a single region of the memory, you can store it in many regions, let's say, many addresses of the memory, in many stalls of our parking. And that region should be continuous. Okay? So for instance, let's assume we want to store a single number. The single number can be stored in a single stall of the memory. Okay? But what if you want to store the Divina Commedia, which is the book of what book? The book of Dante Alighieri. Okay. Well, of course, you cannot store the whole Divina Commedia in a single stall of your park. You need to occupy to store it in a larger part of the memory, and that part of the memory should be continuous. Okay, so the first child will be in the first style, the second child in the second style, and so on and so forth. Is it clear? Are you already, were you already aware of this kind of memory, of storing memory? Yes. Who wasn't aware of this kind of stuff? No.
Wasn't.
Yeah, wasn't. You were already familiar with it, right? So, going back to CPU. Now, the CPU is able to deal exclusively with data which are stored in special locations called registers. Okay? So these registers are, let me say, just like a desk for the CPU. Just think to your home when you are trying to perform your homework, and to do it you take your book from the bookshelf and you place it on your desk and you're working on the book, and then you take back your book and place again on that desk shelf. Exactly the same thing occurs on CPU. So once the CPU needs to achieve some kind of computation of some data, you need to retrieve it from the memory and place it then, let's say, on the register. Then operate on the register, and then after operating on the register, place back the result on the memory. Okay? And this is the idea. So for instance, just to sum up two numbers, you may have to, well, the CPU may have to perform a lot. Are you asking a question? No. Okay. So, let me see if any question. The result after processing stuff with are all devices, input and output, not really. Okay. Okay. No, this is not what I want to do, is this one. Okay, so just to make an example, to sum up two numbers which are already present in the memory, with the CPU need to load the first number in a register, let's say, call it R1, load the second number on the second register called R2, and then evaluate the sum of the two values and store it in R3. And then after that, take the result, take the value which is in the register 3, R3, and place it in the memory. This is all the set of operations that the CPU need to perform to achieve the sum of two numbers. Okay, this is a computer program, more or less. I mean, not written in the CPU language, but this is what is really performed on a CPU to get the result of summing two numbers. Okay, so yeah.
So is the register not part of the memory?
No. No, the register are a part, are stored, are a location inside the CPU itself. Okay, so basically there are a bus moving data from the memory to the CPU, and that data are stored in registers. Okay, but this is exactly what occurs inside the CPU. Now, the kind of operation you can perform on registers, the number of operations you can perform, the number of registers, how fast they are, and I don't know, the kind of data you can store in a single register. All these stuff are dependent on the CPU type. Okay. So the CPU inside your laptop is different from the CPU inside your smartphone, is different from the CPU inside the monitor, is different from the CPU inside, I don't know, your fridge, okay? And depending on the CPU, you have a different number of registers, a different kind of data can be stored inside the register, and different set of operation Because here I'm mentioning all exclusively the sum, but you may think I do not do the exponentiation to multiplication to the square root and everything, okay? And the kind of operation you can directly apply to data inside the CPU depends on the CPU itself, okay? Great. So what kind of data can you represent inside a register and inside the memory? Okay? Well, virtually everything. So, for instance, we can represent letters. We can represent well, this is a Latin letter, but of course you may have a kanji symbol or whatever you want. We can represent an integer number. We can represent, let's say, a kind of real number, and so on and so forth. Now, how can we represent all that stuff inside the computer? Well, as a sequence of bits. So nowadays, the vast majority of computers represent data by using sequence of binary digits. That means that we have a sequence of zeros and ones to represent a single data. Okay? And depending on the context, that sequence may represent a number, a character, or whatever you want. Okay? For instance, to represent the letter A, we have this sequence. Okay? But the exactly same sequence may also means a number. How can I distinguish between a letter and a number? Well, if you go back to your knowledge of a computer, usually the file you are dealing with are equivalent with a suffix. That suffix is a way to say, okay, the data inside this file should represent this kind of stuff. Okay. So if you try to understand what's going on inside a file whose suffix is txt, for sure that file is a text file. So all the data stored inside that file are meant to be letters. So if you find that this number, this sequence of 0 or 1, you know that you have to interpret it as a letter. Okay? But if you try to change that suffix in something different, I don't know, for instance, well, I mean, you may try to change it in something different. You end up with a different result. You may end up with a different result. Okay? This is not always true because usually at the beginning of the file, you have a kind of, how can I say, set of marker saying, okay, this file is properly formatted. But this is the idea, okay? Is it clear? More or less? Have you understood? Have you understood? Okay, great. So the idea is that inside your memory, instead of representing complex data just like the one you can see on the left, you have a sequence of 0, 1. And this kind of stuff are, of course, also represented inside registers. Okay? Now, nowadays, the vast majority of computer usually use 64 bits to represent natural numbers, integer numbers. Okay? This means that the registers inside your CPU are usually, nowadays, are usually able to store 64 bits, each register. Okay. So, if you are asking yourself what means Windows 64-bit or this architecture, this computer is a 64-bit computer and so on and so forth, basically means, look, this CPU has register whose size is 64 bits. Okay? And, okay, you may wonder why it's so important having 64 bits instead of 32 or 16 or... This is just a way to being able to handle larger number. Okay, having 64 bits, we are able to store number up to 2 at the power of 64 minus 1 positive number. Okay, if we are dealing with a 32 architecture, we are able exclusively to deal with number up to 2 at the power of 32 minus 1, and so on and so forth. The very first architecture was able to handle 8 bits per time, and so it was able to handle exclusively number up to 255. Okay, that's it. But, okay, this is a way to represent data. To represent data, we can simply represent them by using a sequence of 0 and 1, but what about instruction? That's the tougher part in some sense. Well, the instruction can be represented exactly the same way. But instead of providing a map from a sequence of bits to the corresponding data, we are providing a map from a sequence of bits to a corresponding structure. Okay? So, for instance, I don't know, just to have a look to this example, in which we are summing up two values, 10 and 2. Okay? As before, to perform this this simple operation, we have to store these two data inside our registers, R0 and R1. Then we have to load the data stored in R0 inside another register called accumulator, which is specifically meant to perform addition, okay, to sum up data. And then after performing this operation, we are required to sum up the value stored in the accumulator with the value stored in R1 with the value stored in the accumulator, and then we need to save the value in the accumulator in the register number 1. This is a way to perform the sum of 10 and 2, and the result is stored in the register number 1. So this kind of stuff are the kind of stuff you are required to perform to get the sum of that two values on the processor named Intel 4004, which, by the way, is the very first microprocessor of the history. Okay. Now, let's see the corresponding bit sequence in binary code. This is it. Okay. So if you look at the first line, the first 8 bit is basically a code saying, look, you have to load these two numbers, so the number represented by the bit going from the 9th to the 12th, this number inside the register 0, and this number, which is the number represented by the bits going from the 13th to the last one in register 1. Okay? This is a way to load the two values, 10 and 2, inside the register R0 and R0 and R1. So the instruction to store these two values inside R0 and R1 is coded by using this code. So the first 8 bits in this sequence are meant to say, look, you have to load the next value inside R0 and R1. Is it clear? Okay. Now, once you have performed this operation to load the value stored in the R0 into the accumulator, which cannot be loaded by its own. So there is no instruction to load the data directly on the accumulator. You have to move the data inside a register and then move the data from that register inside the accumulator. Okay? So that's why we perform this operation at the beginning. Once you have performed this operation at the beginning, so the operation of storing 10 and 2 inside R0 and R1, you have to move the data from R0 into the accumulator, and to perform this operation, we have another instruction whose first 4 bits are used to encode the instruction load the data into the accumulator. So the sequence 1010 is the instruction load Sì, sì, grazie mille. Volevo chiederle, posso usarlo come router di eventuali problemi? Allora magari se il suo contatto sarà sempre remoto, se mi fa il favore di avvisarla e di dirle di chiamare subito lei nel caso ci fossero altri problemi in streaming, cercheremo di risolvere il problema in questa maniera. Perché seguire voi e seguire è un bordelloso, si dice in termine tecnico. Ok. Okay, let's start again. So I would like to start with the person online, people online, but I really didn't understood that the connection was down. I hope that this is the first and last time we experienced this kind of situation. Anyhow, I managed with a colleague of you, one of your colleagues, to warn me in case of problem with the connection. So I hope that we are not going to experience again this kind of stuff. Okay. So going back to our discussion. Am I boring? Yes, I am. Not really. I mean, yes. Thank you for your honesty. I'm spending really a lot of time in this kind of naive stuff, but my intention is to start from very scratch and to use this kind of discussion to reach all the same level. Okay, so in a way we can acquire a kind of common language to talk about really nice stuff. Okay, so the point was before the break we were discussing about how to translate the source code, which are programs written in a programming language, which is a tool to write programs in a human readable way, let's say, into bit of sequence, or better binary code, which is the code that machine use to understand what's going on. Okay, so the programs are executed by computer as binary code, and we need to translate the human readable code we are going to write into sequence of bits. And how can we do it? We can do it by using compilers. Okay, we can use by using compilers. So what are compilers? Well, compilers are simply programs which automatically translate the source code, so the code you are going to write, into sequence of bits, which are executable, directly executable by the computer. Now, there are many kind of different architecture, computer architecture nowadays. For instance, we have mobiles, just to tell some specific architecture. We have a laptop, we have clusters, we have, I don't know, that one is a small computer named Raspberry Pi, and they are all using different kind of CPUs, they have different kind of memories, and so on and so forth. So the point is that, of course, they are all using a different set of instructions and way to represent data as a sequence of bit. However, once you have written your program in a high-level language, just like the C programming language, you can simply recompile your program for the different architecture. So every architecture will have a C compiler, and you can execute your program in mobile, laptop, and so on and so forth. simply by recompiling your source code for the specific architecture. Okay? So the idea is you write once, and every time you want to change the architecture, you simply have to recompile it by using these tools called compiler, which is a program which takes your source and instantiate on the specific CPU you want to use. So very simple. Now, okay, this is what I just told you. So every binary code can be exclusively executed on the architecture for which it was compiled, and if you want to run our program in a new architecture, we simply have to recompile it. That's it. Now, this holds for the C programming language, but not all the programming language works in this way. For instance, there are some languages which decided to avoid compilation. For instance, Python. Okay, so of course you can also compile Python program, but by default the programs in Python are not compiled. The idea is to have a program named interpreter, which basically takes your source code and execute directly on the machine. And these are some pros and some cons, and some adverse, let's say, reason to use. So the pros are, of course, you don't need to compile for every single architecture, because your program can be simply moved from one computer to another computer to a third computer, and all these computers will have their own interpreters, and if you want to execute the program, you simply run the program on that interpreter, so that's all. So you don't need to compile it. Another advantage is that you have exactly the same program for all the architecture. So your program can be moved as it is from your mobile to a server to a cluster to, okay? The program is that piece of code. You can move it directly to another program, to another computer architecture, and execute it as it is. And the third advantage is the executable. So the program that you can run directly on your computer is no more a sequence of 0, 1. So it can be understood by a human being. Okay? And as a negative part of the coin, we need the interpreter. So while if you compile a program, once you have compiled it, you have an executable, you can distribute the executable in any possible computer which implements that architecture. You don't need anything more than the executable. In the case of uncompiled programming language, such as Python, you need the interpreter to execute your code. So it's not enough the program, but you also need some the program that is able to understand what the program is meant to be. Okay, and this is needed for in all the computer you want to execute your programs. Another disadvantage is execution time. Why? Because if you compile your program, you are basically taking your program and you are translating it directly in the language of the CPU. Okay? So the CPU is able to understand it really quickly, let's say. While if you interpret the program, you are basically executing your code upon a layer, which is the layer of the interpreter. So the interpreter needs to understand what you want to do, and then once it understands it, it needs to tell the CPU what you want to do, in some sense. Okay, so you are adding a layer between your program and the CPU, and this layer may delay the execution in some sense. Okay, of course there are many smart ways to reduce the execution time gap between compiled and interpreted computer programming language, but still there is a gap. And finally, usually, to understand what's going on, the interpreter need to allocate memory and space and CPUs, and so in some sense, the interpreted language are usually resource eager. Okay, they need more resources than the compiled counterpart to be executed. So there are advantages and disadvantages. Depends on you. Of course, if you need to write a program that is meant to run on a small probe that should go to, I don't know, Alpha Centauri, for instance, well, probably you don't have much memory, and you are not going to have very resource expensive CPUs, because you need to preserve all the energy for the probe, and in that case probably the best choice is to use a compiled programming language. While if you are going to run your code here on the Earth, and you want to simply, I don't know, analyze data in some sense, and the task is quite trivial, and you don't want to spend a lot of time in programming, and you want to be able to move your program from one architecture to another architecture without any trouble, then in that case probably Python is the best choice. Okay? That's it. Are you still there? So you on YouTube are wondering if there is a full class recorded. Well, unfortunately not, because the recording is on YouTube. So since I missed the link, from the class to YouTube, the part of the lesson which was missing on the streaming is also missing on the recording, unfortunately. Okay, but I mean all the slides are available, and we will see. I mean, I could repeat exclusively for you all the stuff. It depends on how much time I have this afternoon. Okay? Great. So let's move to the next slide. So what we need to develop a C program, well, for sure we need a computer. Unfortunately, we can try it on paper, but it's not really exactly the same. We need a text editor, which is a program to write text, nothing more. And we need a C compiler. And that's all. We don't need, well, we need also an operating system. Well, probably you already know what it is, but I mean, if you bought a computer, probably you already have an operating system, probably. However, actually, this is not really all needed. I mean, you can use, nowadays there are sites that allows you to develop program online, so the compiler is not needed, the text editor is not really needed. You can simply try to connect to repl.it, online gdb.com, or programmings.com. There are tons of different sites that allows you to exercise on computer programming on C online without the need of any text editor, any compiler, and so on and so forth. Okay, you can try to use that. However, we are not, and you are missing the last part of the slides, of course. Thanks God they are able to install the beamer. Of course, we are not really interested exclusively on computer programming. So this course does not only exclusively deals with computer programming, but also introduce some notion of different kind, which will be useful during the DSSC program. And because of that, I rather prefer to, use the old style way of programming instead of using that really nice, wonderful, and really useful sites. Okay. And any question about this? No. Okay. Have you ever used this kind of sites? No. They are great, really. I mean, I suggest you to try them eventually. Okay, so what's next? This is basically the introduction of what we are going to talk. Now we know what is computer. Now we know what is programming language. Now we know why we are writing programming that way and what's going on between our programs and the computer. Okay? And we know why compilers are useful and what's going on, more or less. Now, during the next slide batch, we are going to talk about user hardware abstract layers, which are quite useful way to hide, in some sense, all the details or dirty details with a course on computers, because we are not really interested in, I don't know, how the monitor is working. We just want to use it, and that's all. Okay? So we don't want to have to deal with all the dirty detail like the sequence of bits we saw before. And we are going to talk about operative systems, which, as I told before, probably you're already aware. We are going to talk about POSIX, which I don't know, probably some of you already know what it is, but not all of you, I guess. We are going to talk about Linux distribution, about Linux, which is an operative system, and Linux distribution, which is a way to use and install the new Linux operative system. And we are going to talk about Ubuntu, which is a really specific distribution for Linux, but we are going to talk about it during the next batch. And finally, most probably important things, this is an error, we are going to understand what is a command line user interface, and the acronym here is wrong, should be CLI. Okay, and this is it. Any question? No. Comments about what we saw? Really? Should I go faster, slower? Different things to say? More joke, less jokes? Anything? Okay. Are you still alive? More or less. Here we are. So next batch about next unit, let's say about operative systems and tools. So as programmers, we are not, as I told you before, we are not really interested in all the details about computers. It's nice to understand what's in address, in memory. It's nice, but it's important, not nice. It's important to know what is in address in memory. It's nice to know how CPU works. But I mean, we are exclusively interested in reading data from an input device, just like keyboard, for instance. or I don't know, a DNA sequencer, just to turn on other things, implementing function to operate on data sets. So the idea is that a program is just a function. There are some inputs and you get some outputs. We are interested in performing, in implementing, in writing the program which basically operates just like the function we have in mind. That's the idea. And the last thing we want to do is to provide results in output. So input, output, and implementing function. That's all. All the other stuffs are totally useless for us. Okay? Have you in mind anything more useful than reading data, writing data, and operating on data? I don't have anything in mind besides these three stuff. So, for sure we are not interested in how the input-output device works. So, who cares how keyboard works? I'm not an electronic engineer dealing with keyboards. Okay, I'm using a keyboard. I'm not interested in how a car works. I'm just using cars to come here. That's all. I know I have to put some gasoline on my car, and I know I have to bring to the mechanics from time to time, and that's all. Well, changing tires. Yeah, that's all. Okay? And this is how we are approaching to computer programming. We are not interested in how input-output device works. We are not interested in how data are physically stored in memory. We know that there are addresses. We know that to get data, a specific data we already stored, we can use address to get that data, but where that data is really stored inside the memory and how it's really stored is out of our business. And we are not really interested in how our program will be executed. So once we have compiled the program and we want to execute it, we simply have to run the program and that's all. We are not interested on before the execution we need to load. That stuff is out of our business. Okay, so we need what is called an abstraction layer in some sense. So when you run a program, a lot of wordy things are, of course, inside the computer, but we are not interested in that. Okay, so we need a way to exclusively focus on programs and avoid to take care of the hardware. And this kind of abstraction layer is the operative system. So the operative system is simply a set of programs which allow the user to avoid to take care of the hardware. Okay, if you want to, on your mobile, if you want to execute a program, you simply have to squeeze its icon. That's all. You don't care about where the program is executed. You don't care about how much memory is required to execute the program. You don't care about how much space in the memory is due to execute the program. You don't care about what kind of instruction is used to. All that kind of things are totally useless from your point of view, and so you need an operative system. So the operative system is software that is meant to, well, the first software, usually the first software in a strict sense executed by your computer, which manage resources, so manage memory, disk, CPUs, and so on and so forth. Okay, and what is interesting from our point of view is that the operative system usually offer what is called API, which is a set of interfaces, let's say. to allow to perform operation on the hardware. Okay. So, for instance, let's say you want to write a program to visualize what's on your webcam. So to see the video recorded by your webcam. Okay? You don't have to take care about how the webcam works. You simply have to use the API provided by your operating system to access to the webcam. And that's all. Okay? So that's why the API is quite useful. Now, again, you are missing the last part of the slide. However, there exist hundreds of different operating systems. Are you still there? Speed is perfect. Okay, great. There are hundreds of different operating systems. We have OS X, which is the operating system of the MacBook. We have, I don't know, iOS, that I think is the operating system of, it's called the phone of Apple. iPhone. And you have Android, which is the mobile operating system of Google. You have, I don't know, Windows 10, for instance. You have New Linux, which is the one I'm using here. I don't know, React OS, which is a free operating system similar to Windows, and okay, and all of them provide a set. I mean, may provide us a different set of API. So it could be difficult to write a program which can be compiled to run on all these different operating systems, of course. Okay. However, thanks God, we have standards, okay? And one of these standards is the POSIX standard. So the POSIX standard is a standard which is meant to allow programmers to use the very same API on different operative systems, okay? So the idea beside the standard is that you can write a single program in C, and you can compile it for Windows, OS X, Linux, Android, iOS, and so on and so forth. Unfortunately, not all the operating system implements this standard, but I mean, this is very common implement. Okay? And the IEEE, this IEEE standard, IEEE is the International Engineering, Electronics, and I cannot remember the third group. Okay, and this standard establishes how programs in execution can be created and controlled. So, for instance, if you want to end the execution of a third-party program, how can you do it? Well, the POSIX standard establishes how you can do it. And this besides the operating system you are going to use. So you can write a program which, by exploiting the POSIX standard, is able to end up another program in New Linux, OS X, iOS, and so on and so forth. Okay? The POSIX standard also establishes how data are stored inside a disk, where to place, I don't know, the executable of the operative system, where to place how directory, or I don't know, how do you call it in English? The cartelle. Folder. Oh, okay, thank you. So how the folder are organized inside your operative system, inside your home, and so on and so forth. Another interesting thing from the programming point of view is the C library. So the C library provides a set of a standard set of low-level operation, which low-level function, let's say, which can be used in any POSIX compliant operative system. So, for instance, if you want to compute the square root of a number, you don't have to re-implement the square root of a number, a function that computes the square root of a number in any possible operative system. Why? Because the POSIX standard establishes that that function is already present in the basic standard library in any operative system compliant to the standard. Okay? And that's it. So there are so many other things that the POSIX standard established, but I don't want to go through all of that. Well, so what about, for instance, OS X, Windows, and New Linux, and so on and so forth? Well, OS X, for instance, which is the operative system of Apple for laptop, is compliant to POSIX standard. So while it's not certificate, most of the feature required by the POSIX standard is implemented in the operative system. Okay? So for instance, the standard C library is present, the way in which data is stored inside the disk is present, and so on and so forth. Windows is not, well, I mean, Windows is in Microsoft Windows is in a weird position because Microsoft is aiming at the POSIX standard, but from a certain point of view, but from another point of view, is really don't want to get there. Okay, and so for instance, I don't know. Recently, they made available a new update which allows you to execute new Linux over Windows, but not recently, but at least 1.5 years ago. So you can run the basic function of new Linux over Windows, but to have all the features required by the POSIX standard, you have to do it. So it's not possible to have all the features on the plain Windows, okay? And so it may be the case if you are trying to write a program for Windows. If you try to write a C program, that program can be compiled exactly in the same way on OS X and on New Linux, but to compile it on Windows, you have to slightly change it. Not very much, but not too much, but in some sense you have to change it a little bit. Now, I'm tired. Just the first lesson, I'm already tired. Too old. So, now I mentioned an operative system called New Linux. Probably you already heard about Linux, maybe, but not New Linux. Well, actually, Linux is the central part of the operative systems, what is called the core of the operative system, but it totally lacks some important parts of the operative systems, just like, I don't know, the compiler, just to say one, or the user interface, just to tell you another. Once you buy a computer, you usually, well, it depends on the computer you bought, but if you buy a Mac, Apple computer, usually you open it, you switch it not, you end up with a user interface which allow you to, I don't know, watch video online or movie online or whatever you want. That user interface is a part of the operative system of the Mac, of the OS X operative system, of course. But in Linux by itself does not provide that kind of user interface. So to be able to use the core of the operative system, so Linux, you may also need a user interface. That user interface is usually provided by the new project, which is a project meant to provide all these kind of tools, like compilers, libraries, I don't know, user interface, and so on. So that's why I'm referring to Linux as new Linux, because the full operating system should be called, from a formal point of view, new Linux. Now, this operating system is a free operating system, which not only means that you can download it for free, but you can also play with it, change it, do whatever you want, okay? And that's why the word free is, in English at least, a little bit ambiguous. I mean, in Italian you will say libero rather than gratis, okay? And that's it. Now, since it's a free operating system, of course, anyone can distribute it. So, if you want to buy a license for Windows, you have to buy it from Microsoft. If you want to buy a license, well, it's not possible, but let's assume it could be possible to buy a license of OS X without buying an Apple computer. You have to buy the license from Apple. Well, in this case, since the new Linux operating system is free, there's no one from which you can buy a license. And so everyone is allowed to distribute the operating system itself. Okay? So there are many different sources of this operating system, and they are called distribution. So the distribution are basically customized way to install, handle softwares, and install additional software for the new Linux operating system. Okay? Just to okay. All of them are POSIX compliant, but not certificated. To get the certification, you have to pay. This is let's say, volunteering work, let's say, in some sense. So no one is really want to pay just for a certification. But I mean, in general, they are totally compliant to the POSIX standard. This is a kind of mandatory implicit recommendation for all the distribution to preserve the POSIX compliant, the POSIX standard. So, why we are talking about the new Linux operating system? Well, we are talking about the new Linux operating system because you will extensively use it. Okay, so all the cluster nowadays are mainly based on Linux or something similar on Linux. All the code you are going to write probably should perfectly write on Linux because of the cluster nature, and so that's why I'm introducing it. So if you are not aware about this operative system, don't worry, we are going to investigate it. Otherwise, you are welcome to this program. Okay? Any question? How many of you have already used GNU Linux in any form? Okay, some of you, but not all of you. Are you still there? Online? I hope so. That's the camera. If you are still there, just knock once on the chat, please. Okay. Someone? Yes. Okay, so during this presentation we will focus on one specific distribution. There are really, again, thousands of them probably. We will focus on Ubuntu. It's not the best distribution from my point of view. I don't use Ubuntu, but it's a nice distribution. It's not that bad, and is particularly user friendly, so it's easy to use, and so that's why I'm focusing on it. Okay, but of course, once you have a practice on Ubuntu or whatever you want, you can change your distribution and install a different kind of stuff. Okay, it's just up to you. Now, how to install Ubuntu? So to install Ubuntu, we need a PC with a USB port, 16 GB of free disk space. Are you aware of what I mean by 16 GB of free space? I think so. I mean, probably it's common knowledge. How many of you don't know what I'm talking about when I'm saying 16 GB of free space disk? You all know. Okay, great. A USB key and a network connection. That's more or less all you need to install Ubuntu. However, I mean, this is to install Ubuntu in your own laptop natively, but probably the best thing to do at the very beginning, if you're not familiar with all this nice kind of stuff, is to use a virtualization system. What is a virtualization system? It's a program which basically behaves like a real computer, real PC, and you can use it to simulate in some sense. Well, the word is not really formally correct, but I mean, I hope you understand what I'm meaning. Simulate the behavior of a true computer. So you can install stuff on it without being aware of damaging your own operative system. Okay, and you can use any possible virtualization environment, a free virtualization environment. So free means gratis, not as in speech. So free as in beer and not as in speech is VirtualBox. But actually there is a free as in speech version of VirtualBox, but I mean, you can download also the less free, let's say, version. And if you search for it on Google, if you Google for it, you end up in an Oracle page, because VirtualBox is a project by Oracle. You can download it. It's available for Windows, Linux, OS X, and I don't know, probably also Android, but I'm not sure about it. And you can download it, install it, and then you can create your own fake, let's say, PC on which you can install your Ubuntu distribution. And okay, and also you probably also need a network connection. It would be better to have it, but nowadays it's almost impossible to don't have a network connection. If you don't have it, don't worry, you will have it here during the course. Okay. Now, okay, this is what to do if you decide to really install it on your laptop. If you want to perform a virtual installation, which is the option I suggest to you to do at the very beginning, you need to download Ubuntu, download VirtualBox, create your virtual machine, and so on and so forth. But we will see it during our demo session. Okay? So right now I'm going to perform all the operation I've just told you. Well, I've already downloaded and installed VirtualBox, but I assume you are able to download from the site an executable to install it. I already downloaded Ubuntu, but again, I'm assuming you can download something by... Should I assume too much? I am assuming too much. You seem scared by it. I cannot see your face entirely, but your eyes seem scared. So, is it useful? I mean, if it is not useful to have a demo to show you how to install Ubuntu on a virtual PC, just tell me and I'm skipping this demo. Is useful? Okay, let's do it. It's not that difficult.
I have a question.
Yeah.
Can you do it like on any computer? Because I read that some computers are not compatible with, fully compatible with Linux.
So if you're installing in a virtual environment, is fully compatible for sure. As far as a real, let's say, installation, so not virtual, the virtual one. Of course, there are hardware which is compatible and hardware which is not compatible, but I mean, it's very, very, very difficult to find something which is not supported at all. Okay? Just to tell you the full story, I installed new Linux on this MacBook. It's not quite common for a person to replace its OS X with a new Linux operative system, but I mean it was quite easy, and I didn't even spend I don't know, half an hour to do it. Okay, so let me just show how it works on a virtual machine, and you can judge by your own whether it's difficult or not and decide what to do. But my suggestion again, to the first installation from my point of view should be virtual, the virtual one, and once you get you are confident, self-confident, let's say, in your ability on your Linux, and maybe you have searched on Google whether your hardware is compatible or not. You may try on a real installation if you want. I mean, it's not really mandatory. It's not necessary. And I mean, I worked for many years by using OS X without having any really installed new Linux version. And I mean, it's not.
You can do everything with the virtual machine.
Yeah, I think so. Especially nowadays, because the CPU of the modern laptops are so powerful that, I mean, you can virtualize basically anything. Okay. Depends on you. I decided to replace my operative system simply because I get used to use Linux, and so I wonder why I should use an operative system just to write a virtualizer, to execute the virtualizing and then use my true operative system. But it's up to you. Okay. Yes.
If we install Linux, do we use our own OS?
Can you repeat the question, please?
If we install Linux on the virtual machine, do we use our operating system?
Oh, good question. So your colleague is asking me whether by installing new Linux really on your laptop you are losing your previous version of the operative system. Well, not really. I mean, you can have a contemporary, let's say, installation of your operative system, previous operative system, and new Linux. Usually, if you are used to Windows, so people used to Windows because, I don't know, they use special kind of software which are not available on Linux. It's quite common to have a double installation. And at the beginning, when you switch on your laptop, usually you are asked whether you prefer to run new Linux or Windows. And upon your decision, you end up with the operative system you want. Okay. But I mean, it depends really on you. Because I know many persons who basically delete a whole disk and install one single operative system and use it. Okay. But again, my suggestion at the beginning is to use a virtualization system. Yeah. Yes, please.
I think you mentioned before the WSL, like the Windows subsystem for Linux.
Yeah. Yeah. Exactly.
Yeah. I mean, I'm currently trying that.
Uh-huh.
Do you think that's?
Okay.
Okay.
Okay. I see your point. So let me try to repeat and simplify your question for the audience online. So you are asking. So previously I mentioned the fact that you can run Linux upon Windows, and that stuff is called WSL. Okay, and you were asking whether I'm suggesting to use Linux upon Windows.
Yeah, exactly. I mean, compared to the VirtualBox, if I don't want.
Yeah, I see. So my answer is I rather prefer to suggest with VirtualBox simply because another student, I think last year, had some problems, and I wasn't able to. Well, we weren't able to understand whether its problem are due to Windows, WSL, or Linux. So, from my point of view, to avoid any confusion and to be able to say, okay, this is a problem of Linux, this is a problem on the programming part, this is a problem on the API, this is a problem on the layer you are using, the best thing to do is to use a virtualization system. Okay. Yeah. And to be honest, I cannot recall the problem he had. But I remember that he sent me a program, and he said me I'm not able to compile it, give me some weird problem, and I wasn't able to understand why, because I have exactly the same version of Linux he has, and he had, and at the end it was because of WSL. At least this is my guess, because once he installed VirtualBox, the problem was solved.
Okay. Yeah, because it's working quite smoothly until now, but yeah, it's not so obvious sometimes.
Yeah, that's true.
Okay.
I'm not saying that it's not a good product. I like it, but I mean, since I'm not confident on it, I'm not suggesting it. That's the problem.
I mean, I think it's not a big deal. It's not a big problem.
Yeah. Okay. So let me move to any other question. What about you online? What? Okay. So let me think what's going on here. Desktop. Okay. This is my desktop. I don't know if you can see it. And I'm executing VirtualBox right now. Okay, this is VirtualBox. Now let me create a new virtual machine just for you. Oh, what's going on here? Oh, I see. Okay. Probably I see. Not really. Let me see. Give me a second just to see whether I'm able to fix this problem.